This is our session on upgrading the cloud using modern transport layer security, or TLS for short, which is encryption used to secure your connections to our AWS service endpoints. My name is Janelle Hopper. I am a principal technical program manager in AWS security, and I owned our efforts across AWS to uplift all of our service endpoints so that we require a minimum version of TLS 1.2 or higher. With me today are two of my favorite people I get to work with. First is Stephen Collison, a senior software development engineer and EC2 load balancing team. And then we also have Mark Ryland, who is a director in AWS security. So we're going to go over our agenda here to start, but I would like to know, I'm curious, how many of you care that your connections to AWS, show of hands, don't be shy, are using only the most modern and secure protocol versions? Great, I think everyone. You are in the right place. But before we dive in, as we go through the agenda, I will cover a couple just fundamental concepts just to ensure a shared understanding. Next, I will cover our success story of how we globally updated all of our AWS service public API endpoints to, again, we require TLS 1.2 or higher. Now, by doing this, we raised the security bar, reduced complexity, and simplified your audits. Many audits, as you know, the compliance and regulatory frameworks no longer permit use of TLS 1011. Next, Stephen will cover how we improved your performance by enabling TLS 1.3. He will delve into our carefully planned rollout approach, the unique challenges we face, and how we overcame them. This information can be helpful to you in raising the security bar within your own organizations. Lastly, Mark will cover the future of TLS with AWS, including post-quantum cryptography and QUIC. So let's get started with our first foundational concept, secure AWS connections. Now, this is important because the upgrades we made to the TLS versions apply to every API call you make on AWS. So basically everything you do. This includes downloading objects from your S3 bucket, sending data to Kinesis, or launching your own EC2 instances. So on this slide, I'm going to walk you through a simple, secure TLS connection workflow. So first step, we have your client that is making an EC2 API call, in this case, describe instance, in the US East 1 region. Now, typically your client will be using an AWS software developer kit or CLI, such as the most common is the AWS SDK for Java. It's important to note you can connect also via a browser using our console, which is then just simply proxying the API call to our service endpoints. Now, for the purposes of this talk, I'm just going to keep it simple and use the term client regardless of how you're making that connection, because the TLS behavior is really the same, and that's what we care about here. Now, second, the TLS negotiation between your client and our EC2 endpoint begins. Kicking off this negotiation, your client is sending to our EC2 endpoint in the cloud what is called a client hello message. Now, this is really based on the configuration of your client itself. In the third step, we have our EC2 endpoint, which also has its own TLS configuration, which we call a TLS policy. And as with all endpoints, so not just EC2, all of our endpoints have this TLS policy and will always select the highest mutually supported TLS version between your client and our server. Once the negotiation concludes, the TLS connection is established. Now, this is a two-way secure connection that ensures the data passed back and forth between your client and our server is securely encrypted. Now that the connection is securely established, EC2 will process the call. They will return you the results. And the other thing that happens is the call information is written to our CloudTrail event log. None of this is changing. The only part of this that changes is the TLS versions that are allowed to establish this connection. Now, for our second basic concept we want to walk through just a little bit on the TLS negotiation itself and what is the TLS version that will get used for this session. Again, a reminder, we, AWS, will always select the highest mutually supported TLS version between your client and our server. So what this means in practice is that really your client controls the TLS version that is used as long as it is one that we support. Now in this version, we have the old obsolete clients like those built before 2014. In that case, the client is not capable, as you can see, of TLS 1.2 or 1.3 or higher. And because now we, on the service side, have removed support for TLS 1.0 and 1.1, as you can see, there's no mutually supported version, and this connection will fail. Now, this really illustrates the connectivity risk, the availability impact risk to some of you as we gradually made these updates to remove that TLS 1.0 and 1.1 on our server side. It's also important to note that we did not make these changes because of any security risk to you. Now, it is true that in the wild there are known security vulnerabilities with TLS 1.0 and 1.1. I'm sure you've all heard of Poodle, Beast, and others. It's really important to understand that AWS has mitigations in place for those issues, so your data was still protected. We also offer additional layers of protection as we use the SIG-v4 protocol within the TLS session. SIG-v4 ensures request integrity because the request content cannot be changed without breaking the request signature, which would then fail the call. Also with SIG-v4, there are no reusable secrets, such as bearer tokens. Now, for the majority of you, you were already on modern clients, those built on or after 2014. So you were already connecting to us using TLS 1.2 by default. And then as we enabled and added TLS 1.3, you just auto-magically started using TLS 1.3. There was no actions you needed to take, and as removed 1.0 and 1.1, there was no risk of service disruptions to your workloads. So now that we covered the core concepts, let's talk about some more of the fun stuff and how we removed TLS 1.0 and 1.1. So one more show of hands. Curious how many of you, before you came to this talk, were aware of our announcement in a security blog post that we were doing these actions to remove 1.0, 1.1, and that we had successfully completed? Just a few. Well, great. Glad you're here. For those who didn't know, yes, we've done this. We finished in February of just this year. It was nearly a 2-year-long effort to raise the security bar and simplify your audits. Now, for those subject to compliance and regulatory standards, this does mean that now you can very confidently run your audit scans with no concerns of findings related to these old, outdated TLS 1.01 versions, which are really no longer allowed by most standards. Now, as an industry leader serving hundreds of millions of your connections every second, we thoughtfully and diligently approach this change. We did this in a way to limit the connectivity impact risk that we talked about in the previous slides for those who are on older or custom clients that did not yet support 1.2 or higher. Now, to give you a better sense of the scale of these changes, and this applies not only to the deprecation side, but later when Stephen comes up about enabling TLS 1.3 as well. So the changes that we made were to over 9,000 service public API endpoints for over 200 global services, which all now require TLS 1.2 or higher. Now, over the course of the effort, we detected over 185,000 of your accounts that were still using the TLS 1.0 and 1.1 versions. This seems like a really high number, but just to give you an idea of the scale of AWS, this was really a fraction, sorry, there's a bug, of the overall connections that we have. So the fraction was like 0.01%, 185,000 accounts. But that's still a pretty significant number, as you can see. Now, as I mentioned, to minimize the risk of service disruptions, we roll this out gradually on a server-by-server basis, doing this almost nearly 2 years, with the final service finishing their deployments to make these changes in February of this year. One exciting note, I think, is per our recent testing, it appears that we are the first major cloud provider serving hundreds of millions of global customers to successfully remove these outdated TLS protocols. And given we are such a large player in the industry, this is really pulling the entire industry forward. Now, we want to thank all of you, especially those of you who did need to take actions and make changes to update your software so that you did not have any connectivity impact there. And so thank you to you all, as together we really achieved this important progress. Now, I just want to touch a bit on the work we did in terms of minimizing the impact risks to those 185,000 accounts we detected on those outdated versions. As you can imagine, the key to this was really data, data, and more data. Really, namely what we called TLS impact data, which is really just what is that negotiated TLS version that gets used during the session and which of your accounts were using that version. This was really central to our work to be able to identify these accounts and then notify you and engage you so that you had time to make the needed changes and avoid any workload disruptions. Now, to this end, what this diagram is showing is that we built our own serverless big data pipeline, of course, using our own AWS services. The data that we used to identify the accounts and find them that were using TLS 10111 was primarily sourced from CloudTrail, and then we also used some service logs as well. And just given the scale of AWS and how many connections we process, this meant that the data platform itself was processing over 800 billion records per hour. So it gives you some idea. Now, of course, I do also want to mention we meticulously locked down this data with various security controls to ensure we maintain data privacy. Now, for the pipeline itself, just kind of looking at this diagram, we used Amazon Simple Storage Service, S3, for our storage. Then we used Glue to categorize and transform the data so that it was available for querying in Amazon Athena. We were able to regularly run our Amazon Athena queries to ongoing throughout the effort, identify those accounts that were still using the outdated TLS 1011 protocols. Now, we also partnered with AWS support, and each time we ran this, which at least monthly, we would pull out these accounts and send ongoing notifications to each one we detected until they were no longer found in the data set. So these were sent, the notifications were sent to your AWS health dashboards, plus your emails. And we sent over 200 of these, 200 rounds of these to all these accounts over the course of the effort. One other important note about the notifications is they also contain important metadata, such as the user agent, source IP, and other, because we understand you have really large environments and we want to make sure that you could identify those clients that needed to be updated. Now, one last thing before I hand over to Stephen, I just want to touch on one innovative solution that is really important for those cases where the clients could not update. So in those cases where the client could not update it and you needed to maintain connectivity for TLS 1011 connections, which was most common, we saw this a lot with S3 and callers to S3, often embedded devices, points of sale, chips and devices, and so on. In this case, what you can do is use a proxy, such as Amazon CloudFront, which will sit between the callers and the S3 bucket. And what CloudFront provides is a per customer, per distribution TLS setting that you can control. So this means that you can set a TLS 1.0 policy on your own CloudFront distribution, allowing those callers to still connect using those older protocols. And then the calls transform between the proxy and Amazon S3 so that it's using TLS 1.2 or higher. This allowed you to maintain the backwards compatibility and for us to move forward in updating the service API endpoints. The QR code linked on this slide has a lot of details on how you can set this up. Now, deprecating TLS 1.0 and 1.1 were not the only amazing things that we did. We, in parallel, also enabled TLS 1.3, for which I'm going to hand over to Stephen.
Thank you for showing up early this morning. I know it's not easy to wake up early. I can attest to that. So as Janelle said, my name's Stephen. I'm a software engineer in our Elastic Load Balancing organization in AWS. And I work a lot on our public-facing products in ELB, which is Elastic Load Balancing, on TLS termination. On TLS termination on our public-facing products. I also work on some internal libraries and applications that implement TLS termination, as well as S2N, which is our open source TLS library that AWS uses. I'm going to talk to you about why TLS 1.3 matters, how we did the migration safely, and then also some actions available for you if you want to add TLS 1.3 to your endpoints that you build on AWS. So what is TLS 1.3? Janelle mentioned how removing TLS 1.0 and 1.1 raised the security bar for you when you connect to AWS. I kind of like to think of it as raising the security floor, because by removing the ability to negotiate TLS 1.0 and 1.1, even though there's no active attacks against TLS 1.0 and 1.1, it's just cleaner from a system perspective to never be able to negotiate them. But the other dimension of how we were thinking about the recent cloud uplift migration for transport security is also raising the security ceiling. And that's how I want us to think about TLS 1.3. By adding TLS 1.3 support to our endpoints, it's really raising the security ceiling. And the other way I like to think about TLS 1.3 is that it's sort of a refactor of the protocol. There's significant changes made to the negotiation that remove old modes and also provide an opportunity to negotiate future algorithms that Mark is going to talk about later. More of the handshake is also encrypted, but if there's any terms on this slide that don't make sense to you or are a little bit inscrutable, I'm not going to go deep into the individual algorithms removed or in the individual threats that are being prevented. The other thing I want you to keep in mind is that even though we're adding TLS 1.3 and it's a preferable protocol, our TLS 1.2 implementations and configurations are still hardened against known attacks. So besides security, TLS 1.3 also brings tangible performance improvements. So Janelle mentioned earlier that every TLS handshake begins with the client hello, and the goal of the handshake is to agree on a symmetric secret. In TLS 1.2, this was achieved with 2 network round trips because one network round trip was used to agree on a key exchange algorithm, and then a separate network round trip was used to actually exchange key material for key agreement. TLS 1.3 improves this by collapsing those 2 operations into one by having the client choose a key exchange algorithm it thinks the server will support ahead of time. Effectively, this just means that we save one network round trip for every new connection over TLS 1.3. And if you have clients that are connecting over longer network links, such as a mobile client in this diagram, you're going to see a significant improvement. And if you're connecting in region in AWS from your own VPC, you're going to still see some improvement, but it may not be as pronounced. So as I mentioned earlier, TLS 1.3 is a significant overhaul to the protocol. And significant network level changes increase the likelihood of compatibility bugs. And when I think of AWS API endpoints, I think of the multi-tenancy and the heterogeneous clients that connect to our endpoints. And when new engineers onboard onto my teams, they often ask me, why is transport security difficult? Why is TLS hard? And I think TLS shares a lot of the same challenges as other areas of security. We have the challenges of secure development. We have the challenges of hardening configuration. We have the challenges of patching. But I think one area that's unique for TLS compared to other areas of security that I work in is this heterogeneity of clients that connect to our endpoints. And the heterogeneity of clients that connect to our endpoints means changing our endpoints is very difficult because we need to make sure our endpoints are compatible for every possible combination of client behavior. And at the usage scale of AWS, we effectively see every possible permutation of client behavior that exists on the internet. TLS for AWS is a bit of an open system. It's not a closed system where we have complete control over our customers' network stack, nor do we want to. It's open and clients can connect to AWS using the network stack that exists in their systems, whether it's a browser or an embedded device. So hopefully you can kind of see how I'm framing the challenge of doing this migration, which really is migrating that multi-tenant set of traffic coming into our endpoints. Before we do any production changes to our endpoints, that challenge is solved with development. So in AWS, development starts with S2N for TLS. And when we were developing S2N originally, we were aware of the compatibility needs of AWS. And our strategy to help get assurance that when we made development changes in S2N, we're still compatible with our customers, we added a suite of integration tests that cover well-known clients. And this gives us a pretty good base level assurance of compatibility that we would otherwise not have if we just did some development and went straight to production. Now, this assurance is good, but it doesn't quite give us all of the assurances we need. This is not the last slide that I'm going to be talking to you about, so clearly there's more complexity. So next, I want to talk to you about a high-level pattern that we used to actually roll out production changes for our API endpoints. So there's a high-level set of items here, and I want you to imagine that there's an individual AWS service team that's executing each of them. We're going to go more deeply into each item in this list. So before a service adds TLS 1.3, we do what we call proactive risk monitoring. And the way this works is we have a corpus of known risks that we've collected throughout both the rollout of TLS 1.3 and also from information we've gathered in industry based on known client issues or compatibility issues in TLS 1.3. And we use this corpus to compare against existing traffic coming into an API endpoint before we even add TLS 1.3. And if there's any and we compare this corpus against the API endpoint's traffic, and if there is a risk detected, we write it to a centralized metric store that the API endpoint can use to sort of block the rollout because there's an impact risk. And this approach actually works because the impact signature is often in the client hello message, which is roughly the same between TLS 1.2 and 1.3 because clients effectively send the same message. So once an API endpoint determines that there's no proactive risks according to the corpus that we've created, we start doing a gradual rollout. And in AWS, we have some standard deployment safety mechanisms that we use and deployment safety principles, which the goal is to minimize blast radius and to ensure that there's no correlated failures. And as part of our standard deployment model, we typically isolate changes at the availability zone level or smaller, such as at the cell or individual host level. The diagram here is showing how hosts behind a load balancer may have different TLS configurations, and that's one way to roll out this change. So I mentioned earlier that updates were seamless for a majority of clients. And this creates a monitoring challenge if there's any issues for a small subset of clients. We found that this is an issue because if there's an issue for a small subset of clients, their failure rate may not meaningfully change the overall success rate into our multi-tenant endpoints. So the graph on this slide is showing how the blue line represents a success rate graph on one axis, and the green line is a failure rate graph on another axis. You can see if there was an issue, and this represented an issue that we found in one service, the blue line doesn't appreciably change, but the green line does. So if you can believe that success rate monitoring is insufficient, we found a few additional approaches that were more advanced that helped us detect issues as we were rolling out 1.3. The first approach that we took was to monitor rate of change of failure. And a challenge that we have on our API endpoints is that network weather and scanners actually create a baseline level of failures that we always see on our endpoints. So that green line on this graph is showing that failures are always elevated, even though we're not actually making any changes and they're not actually causing any impact. But we did want to monitor the rate of change. The second approach we took was to measure drops in success for individual client identities. And we measured drops in success by looking at the HTTP user agent. And if any HTTP user agents dropped off significantly after we added 1.3, it implied that we impacted one group of clients specifically. So we used the previous slide to implement a monitoring approach. And for long tail issues, we typically will just roll back. Even if we have a suspicion of impact in AWS, our approach is to roll back and ask questions later, whether it's a big issue, a small issue, or even a suspicion of an issue. And for TLS 1.3, rollback is effective, but it's a very blunt tool. It means that all of our clients, all of our multi-tenant, all of the entire heterogeneous set of clients connecting to the API endpoint no longer get TLS 1.3, and we talked about the benefits earlier. So if rollback was a blunt tool, we wanted something that was more precise, more of a scalpel, because issues are isolated to individual clients or individual buckets of client identities, as I call it in this slide. And we created a new approach called sidelining, which is much more of a targeted rollback to individual client identities that we determined to have impact. So first, what we did was identify the client identity identifier that is having impact. And one example of an identifier is an individual domain name or resource name that is experiencing impact. And then we would set a rule on our API endpoints to keep that identity on TLS 1.2 so that we could move forward for other clients. Domain name is a simple example, and in the diagram here, I'm using foo and bar as examples of two different client identities where foo has impact and bar does not. But there's also more advanced identifiers you can use, such as identifiers in the client hello, which may uniquely identify an impacted revision of client software. And really our approach was to pick an identifier was to sort of best fit detecting impact with moving clients forward. So if we found that the best course of action was to use the client hello because it's a specific software version, we would do that. Or if it was isolated to a specific customer or resource, we would do that. So sidelining helped us move forward. It was a very precise mechanism to remove impact for individual clients, but long-term it's not ideal because we don't want to keep customers on TLS 1.2, even though it is known to be secure. We do want to give customers the opportunity to negotiate 1.3 as much as possible. So our approach, whether we were rolling back or sidelining, was to reach out to customers, and we have our corpus of client-side risks that we used to give customers actions to update their clients. And the actions that customers took were typically to update their clients or change their configurations on their clients. But occasionally we would work with customers or we would do root cause analysis and reproduction, and we would find that it wouldn't be possible for customers to update clients in a widespread basis. So what we decided at least 5 different times was to change our server-side behavior to securely accommodate clients and allow them to connect over 1.3 by changing our server-side behavior. And we made sure that there were no security trade-offs with each of these changes. One notable issue that we encountered was with a very popular programming language's standard network stack that broke after transferring 140 gigabytes of data. And obviously this is very intrusive for storage services or large data transfer services. And we were able to turn around a fix on our server side by changing our behavior in a way that allows those broken clients to continue to connect without having to make any changes on the client side. And we were able to deliver a workaround on the server side before there was even a fix available on the client. And I think there's still an open bug tracker for that issue. But those clients are still able to connect to AWS today and send as much data as they'd like. So now that our server-side changes are complete, a majority of clients connecting to our AWS API endpoints are now using TLS 1.3. It's around 80%. And that's a vast majority of connections coming into AWS. And transitively, if it's a vast majority of connections into AWS, it's a non-trivial amount of the internet's traffic that we migrated. We expect that the remaining 20% are clients that are either old or they're explicitly opting out of TLS 1.3. So if you want to make sure, if you're concerned that your clients might be in that 20% and you'd like to not be in that 20%, there are a couple options for you to go and take to one, check if you're negotiating 1.3, and also some actions for you to take in case you want to make sure your clients are on 1.3. So the most clear action to take is make sure you're using the most up-to-date AWS SDK for Java if you're using Java, and also look out for explicit parameters you might have set in your configuration to either restrict algorithms or protocols that may be incompatible with TLS 1.3. Now, if you have an organizational need, security need, or any other need to stay on TLS 1.2, you can do so. We're going to continue to support TLS 1.2 for the foreseeable future. So we talked a lot thus far on how we made this big change to our AWS API endpoints, and hopefully you can see now that it's been successful. 80% of connections are now using 1.3. I also want to talk to you about if you build endpoints on AWS for your services, how you can get 1.3. So if you're using Amazon CloudFront or Amazon API Gateway public endpoints, 1.3 is on by default. You don't need to take any additional action. There are additional controls on these services if you want to take other actions, but 1.3 is on by default. So if you use Elastic Load Balancing products, there's a few additional controls available to you to sort of match how we were thinking about the safe rollout for AWS. So I'm going to walk through the additional controls available, and you can use as many or as few of these as you like based on your own deployment safety and rollout approach. So for Elastic Load Balancing, what you would do is you would choose a security policy which enables TLS 1.3 or any other parameters you're interested in, and you can do this at your own cadence, and you can roll it back at your own cadence, depending on your needs. And the diagram in this slide is from the console, the dropdown for how to select security policy. So during rollout, ALB and NLB support CloudWatch metrics, which measure client TLS negotiation failures. So similar to how I was talking earlier about monitoring for failure, you can use this metric for the same, and you can attach a static CloudWatch alarm on that value. You can even attach a CloudWatch alarm based on anomaly detection for that value. There's also access logs and connection logs for ALB and NLB that allow you to dive deeper into client connectivity, such as looking at user agent if you're using ALB. Once the TLS migration is complete, one new control that we launched last year allows you to ensure that your infrastructure never regresses and accidentally disables TLS 1.3. And the specific thing we launched last year for ELB are IAM condition keys for security policy. And the way this works is you can write an explicit deny policy on IAM that denies security policies that you don't want to use across your account. Or if you have a central security team, you can do it across an organization using a service control policy or an SCP. And this is a pretty powerful tool in case you have developers or you have yourself and you're provisioning new infrastructure and you don't want to accidentally provision something that has an older security policy. When this policy is attached, the ELB API will reject any calls that use one of the security policies listed that are not allowed. In the diagram here, I have a policy that I cooked up in a few minutes prior to this talk that denies any ELB security policy that does not enable TLS 1.3 and does not remove TLS 101.1.1. But you can craft your own according to your organizational or security needs, such as if you want to ensure that only FIPS security policies are used, you can write an IAM policy that ensures that. So that's all from me. Thank you, everyone. Hopefully you can see how we did this challenging migration in the cloud for our AWS API endpoints, and also how you can achieve the same for your endpoints. Next, Mark is going to talk to you about areas that we're looking into for the future of transport security and TLS. Thank you.
My name is Mark Ryland. I'm a director in the security team, and it's great to be here. I'm going to change my screen here so I can see the next slide a little better. And we're here to talk about some things around the future of TLS. Now, let me give a little bit of a backstory. So, my colleagues that you've been hearing from, they did a tremendous amount of work in this migration effort. It was absolutely amazing to watch the level of activity, the details, the analysis that went into maintaining consistent experience for clients, not breaking our customers. And I'm really proud of how much AWS does to work in that fashion. But they did a ton of the work. I was kind of a little bit involved as a little bit of a advice giver, a little bit of customer interaction, helping with what they were working on. But one thing I will take credit for, and that is this talk, because I thought that was so cool what they had done. I wanted people to hear about it. So that's something I hope you'll appreciate. So my job here is to talk a little bit about the future aspects of TLS. And in particular, two areas: post-quantum crypto, which is coming. It's here today, but also will be a much bigger deal in the future, as well as some enhancements in the HTTP area with a new version of HTTP called HTTP 3. So let's talk a little bit about post-quantum. So to talk about post-quantum crypto, we should talk about quantum computers briefly. So what is quantum computing? As you're probably aware, a new paradigm for computers, a ability to use a new kind of computational concept called a qubit, as opposed to our traditional ones and zeros. You have the notion of a superposition, and the theory of quantum computing, which has been proven sort of through academic and mathematical analysis, is that you can do all kinds of interesting computations with quantum computers that are either not possible or impractical using traditional computers. The expectation and hope is that you can solve all kinds of new challenges that, for example, in especially things like modeling nature, right? Physics and chemistry, you can imagine, and all the researchers are working on ways in which you can greatly enhance computation regarding natural processes. And there's other mathematical capabilities that quantum computers will have, and scientific capabilities. So there's a lot of energy and a lot of investment in the future in quantum computing. AWS is working in three main areas, I would say. So first of all, we're working on quantum computing. So we have both a service today, the Bracket service, I'll talk about in a second. We're also doing fundamental research in the area of quantum computing. We're working in the quantum networking space. But finally, those are kind of like the positive things you do with quantum computers. But there is a negative, which we'll talk about, which is we're working on post-quantum cryptography. And again, we'll get into all these details. Now, there is a caveat, which is when will there be a sufficiently capable quantum computer to do these amazing things? And it has historically been a little bit of one of these things, like it's always 10 years away, right? Like 10 years ago, it was 10 years away. Now it's 10 years away. However, that said, there has been a lot of progress, and I would say it's probably not a good bet to bet against well-funded engineering teams, which is really where we're at now, is a lot of both startups and large companies such as Amazon really investing a lot in going after this problem. And when we get to the point where we have a quantum computer with a sufficiently large number of coherent qubits, ones that are protected from the noise, which is the hard part of all this, you can expect this to happen some 5 to 10 years in the future, and we'll derive these benefits. But we'll also create the risks that we're going to talk about. So, yeah, before we move on, there's this cool picture you can find on our website of a actual computational unit that we're developing in our research labs. So what are the positive things here? What are we doing to develop quantum computing? First of all, we have a service today called Bracket. So Bracket, think of it as an API framework, set of traditional AWS Amazon Web Services capabilities. As you would expect, you can create a Bracket instance. You have the usual controls using IAM policies, all the standard stuff. But in the end, what you're doing is you're able to essentially submit jobs to quantum computers to get results. And your teams who want to develop an experiment in this space can access not just one, but a variety of different kinds of today's quantum computers. And we do that through the service. So what can you access? So we actually partner with existing companies who are in the process of developing quantum computers and provide as a service access to their hardware. So think about it. It's unlikely that you're going to want to go and buy one of these very expensive pieces of hardware, but you may well want to experiment with one, learn about them, test them, see if there's algorithms that you can come up with that will be beneficial to your business. Bracket is the perfect way to do that because you're essentially paying per use in a classic cloud computing manner and not having to purchase a bunch of expensive hardware. So we partner closely with these companies to create secure connections between our facilities and their facilities, security around the computational properties, and then you can experiment and play with the different quantum computers that are out there. If you're interested in this, I'll put up a QR code. We have a whole team in our solutions architecture function. It's called the Quantum Solutions Lab. You can actually take that back, reach out to your AWS sales team, and get in touch with these folks, and they will provide you with some essentially free consulting to see if these current and maybe future technologies could be helpful for your business. That said, today's quantum computers are not as powerful as we believe they need to be to really achieve some of the goals that are part of this effort. So we also do fundamental research. And a few years ago, we established a joint research center at Caltech in Pasadena, California. There's a picture of the building there in the foreground on the lower right. Again, there's a lot of information on the web if you'd like to learn more about the fundamental research work we're doing. And finally, on the positive side, what good things you can do with quantum technology. Quantum networking is a very interesting area. There's been a lot of research there, but also there are products in market today that use the concept of entanglement, the idea that you can have these quantum arrangements between particles such that if you perturb one, you perturb the other. Spooky action at a distance, it's sometimes called. But that property is very intriguing because it allows essentially a possibility of communication that cannot be intercepted by an adversary. So things like key exchange potentially can be greatly improve the security of those things by the use of these quantum entanglement to propagate sort of secrets in a way that is not susceptible to any type of person in the middle attack. So that's an area where we're also working, and again, you can learn more about that. So I had to tell you all the good news in order to talk about the bad news. And the bad news is there is, if and when these sufficiently powerful quantum computers exist, the experts agree that our current cryptography that we use, especially for networking, is in trouble. So if there were a sufficiently powerful quantum computer, many years ago, mathematician Daniel Shor developed a proof that a powerful quantum computer could brute force crack asymmetric cryptography. So the type of cryptography we use today, again, especially in networking. It was initially proven with RSA protocol, so that was based on the relative impossibility of calculating, of dividing the product into two very, very large prime numbers. That was the kind of the original design of asymmetric crypto. Later, other technologies came along, including elliptical curve, most notably, which is kind of the current state of the art. And subsequent research showed that that too is susceptible to quantum attack. So it's important to note, however, sometimes I work a lot with policy people and various people in government and regulators. And the word has sort of got out, oh, watch out, the future is in risk because of quantum computers and cryptography is broken. That's not true. Symmetric cryptography is relatively safe. There's no indication that today's symmetric crypto that we all use for block storage, S3 storage, databases that use something like AES 256 or block ciphers, it's likely that quantum computers could brute force those algorithms more quickly than regular computers, but the speed up is only 1,000 times. It's not nearly enough to make it practical to crack those protocols with a quantum computer. So that part of our crypto world is relatively safe. The unsafe part is asymmetric cryptography, which is what we use a lot in the networking space, because the key property of an asymmetric crypto is I can transmit a secret to you without sharing a secret with you. That's the key. That's why we use it to sort of bootstrap our connections across the network. Now, it's also much more expensive computationally, et cetera, et cetera. So as is implied or stated in the earlier part of the talk, one of the very first things that happens once you are able to create that secure channel using asymmetric cryptography is you exchange a symmetric key. And then you use the symmetric key to actually do the encryption of the data because it's just so much more efficient. But with things like forward secrecy, you're constantly rotating those, et cetera. But in the end, you're using symmetric. But that outer boundary is, and that sort of bootstrapping is what's at risk with quantum computing. So here's the threat model, at least for now. Imagine a sufficiently motivated and sufficiently resourced bad actor who has somehow access to packets flying across the internet. And of course, that's not at all unlikely or impossible. In fact, you've probably seen pictures of things like special submarines that governments own that can go to subsea cables and maybe do some stuff. And they can't trivially see encrypted traffic, but they could potentially siphon off encrypted traffic and record it. So if I could make a record today of your encrypted data, and again, I had the belief that this could someday be very valuable, once a quantum computer comes along, I could take that recording I've made of data, of encrypted data, I could crack that outer shell, which is the asymmetric crypto, pull the symmetric keys out, because now I have those in plain text, and I could decrypt the rest of your traffic. So again, is this a real practical risk? It's debatable. Maybe there's certain locations around the buildings of intelligence communities or centers or something where someone might be motivated to do this. Probably not your Twitter traffic from your mobile phone is not likely to be. But of course, if you're doing an attack like this, you're sweeping up everything, right? You can't discriminate between different users of the connections that you're siphoning. So again, this is the sort of theoretical risk. And you might say, well, gosh, that seems pretty impractical, and it kind of is. But the problem is, if we don't start working on this problem now, by the time the risk becomes real, it'll be too late because of the difficulty of upgrading all our systems, which we've just been hearing about. So we really have to focus today on building systems that are safe against this threat, such that when the threat develops, it's not a crisis. So you can think of that as what we're about to talk about in terms of post-quantum. So what's the history here? In a nutshell, problems identified way back, 30 years ago. Academic and government people started talking about this, meeting and having academic conferences on this issue, this threat, 20 years ago. Then 10 years ago, you begin to see actual work done to see what can be done to solve the problem. And here's a list of some of the activity. And really in the last 6 to 7 years, there's been a lot of very focused activity to develop and standardize new mathematical algorithms which cannot be brute forced by a quantum computer. And there actually exists today a preliminary winner of one of the different kinds of, there's different algorithms that will be standardized. Some will optimize speed over CPU and memory. Some will do the opposite. There'll be 3 or 4 of these probably in the next few years. And for different purposes, some for key exchange, some for other parts of the PKI system that we all need to upgrade. But the current kind of winner of the key exchange protocol is something called Kyber. So that's out there as a sort of preliminary winner, and the final standards for a couple of these for this round will be announced by NIST later this year. By the way, for customers outside the U.S., NIST convened this project. The submissions came from all over the world. It's a completely global project. It happened to be sort of managed by an arm of the U.S. government, but it's not, as far as I can tell, it's not perceived as a U.S.-centric thing at all. It's seen as a very much an international effort, and will be standardized in IETF or potentially ITU or something like that when it's all done. So what have we been doing? So we've been very engaged in this effort from early days. We've had our cryptographers were involved in some of the submissions to the NIST, what I'll call a beauty contest, who's got the best protocols, judged by other cryptographers in a very collaborative and sort of a cool academic contest. As soon as the first winners were announced, we actually had been working on implementations, open source implementations, and we actually have now deployed those, and I'll talk more about that in a minute. But the first Kyber was announced, and one other one in July, and even later that month, and then the following month, we actually put into production on 3 service endpoints the ability to do this, what's called hybrid key exchange. So a hybrid key exchange means that the initial secrets are passed using a combination of today's elliptical curve technology and a post-quantum algorithm. The result being that even if the post-quantum algorithm, being new and not terribly battle-tested yet, even if it turns out to have some flaw, you'll still get the same protection you would have gotten if you hadn't used it, because you're also using the tried and true and elliptical curve, and vice versa. The quantum algorithm can protect you in case there's some weakness or there was a quantum computer invented which would be able to crack the elliptical curve. So that hybrid key exchange will be the norm, I'd say, going forward. You might ask, what about performance? Here's a couple of screenshots from a blog post you can easily find, kind of comparing, in this case, latency. And this is purposely sort of, realistically out of scale. Most of the latency comes from the network round trips, and that reflects the fact that even though these hybrid key exchanges are slower, they're not going to have a dramatic impact from kind of a percentage basis. And you can see that the hybrid key exchange takes about 30-40% longer in terms of millisecond delay. And if you look at the bandwidth requirements, there's a little bit more of an impact. The amount of data that needs to be exchanged is a bit higher. But again, in our modern networks, a few thousand bytes shouldn't be too problematic in most situations. So that gives you some indication of what will happen in the future as we begin to move to these hybrid key exchanges. So what do? We take action. I've already mentioned a bunch of these already, but just to summarize, working on the algorithms, working with the standards bodies, collaborating with a bunch of other players, and open sourcing all the work we're doing, by the way, super important and valuable. People, to minimize the number of people that have to go build their own versions of these things will, and like with many of our technologies today, when we do the open source implementation, we're using formal methods. We're using, the computer science area, a formal verification to not only, using things like Rust to minimize certain classes of bugs, in terms of the programming language, but also proving the correctness of these implementations, which is really valuable. And as I mentioned, if you have a hybrid key exchange compatible client today, which you can build and download using our open source software, even today you can walk up to 3 of our services and actually use a post-quantum algorithm. So KMS, Certificates Manager, Secrets Manager. Why do we pick these 3? Well, these are somewhat unique services in that they do have APIs where you literally send us very valuable secrets on the wire. So for example, you can upload your own entropy for KMS, essentially your own encryption, root encryption key. Certificates Manager can involve, exchanges of private keys, which are very valuable secrets. And of course, Secrets Manager is a secret store. So these are places where if you're going to want to protect against some future quantum threat, these are good places to start. Quick takeaways. So we're executing on this on behalf of customers, open sourcing our work, so you can both see what we're doing, but also take advantage of that, working with standards bodies. Actually, perhaps most important is the lessons that we learned from the 1.3 migration, the deprecation to 1.0, 1.1, and the upgrade to 1.3. This is really valuable information for us to develop the tools, technologies, concepts to enable safe rollout of future algorithms, which no doubt will cause compatibility problems. And even today, we've seen that hybrid key exchange of PQC has caused compatibility problems. We've seen tests in other environments where, for example, a lot of network firewalls are very confused by these very different kinds of packet sizes and so forth, and they actually malfunction. So it'll be a bit of a long road and a grind when the time comes to start moving the industry forward to this. We'll figure out a way to do it. But we've learned a lot of lessons about things like sidelighting and how to do this at scale. And so we can apply those same learnings in this case. So then very briefly, as we finish up the talk, I'm going to talk about HTTP3 and QUIC. So hopefully everybody knows this history, at least at a high level. HTTP, been around a long time. Had the property in the early days of just using TCP to do all the packet ordering and connection management. Textual encoding, all this stuff worked great, but as time went on, people began to be frustrated by the performance overhead of how the HTTP protocol worked. So 1.0 came out, 1.1 came out and made some improvements, especially the ability to reuse the same TCP connection for multiple requests, but it still had a lot of issues from a performance perspective, including things like head of line blocking, because you make a request, you had to wait for the response to that request before you can make another one. And so people who build web browsers especially were getting frustrated by these performance limits. So they invented HTTP2, a nickname was Speedy, and this allowed for a lot of new optimizations of how HTTP works. First of all, binary encoding, you wouldn't have to resend the same data over and over again on the same connection. So like cookies would be exchanged multiple times, so you could reference a previously exchanged item, decreasing the size of the packets, increasing speed, and multiplexing in server push. So if the server has a web page and you do a get for that web page and the server looks at that web page and it's got 100 gets embedded in it, which they often do, the server could just start sending you all the data that it had corresponding to all of those things, and the client would understand, oh wow, okay, I asked for X, but I'm going to get X plus 100, and that could work and massively increase performance and decrease latency. But in the end, the TCP protocol itself kept getting in the way because of the way it works. So if you look at HTTP3, essentially what's happened is that the whole stack below HTTP has been re-engineered. UDP is used as the fundamental transport, and the HTTP protocol itself, or the part of it called QUIC, has re-implemented TCP, all of the things you need, packet ordering, packet numbering, loss detection, congestion control, all that stuff has been re-implemented within HTTP, because if you know the semantics of what you're trying to achieve at those higher levels, you can really optimize like crazy for, at the lower level by using a more primitive, if you will, abstraction. And this is, to me, a great example of layers getting in the way. We have to use layers in this industry, right? Nobody writes, very few people write machine language. We all use compilers. We've noticed recently the difference between a processor architecture and the microarchitecture because of all the side channel issues that have arisen. The processor promises to do a whole bunch of things, but actually it does a whole bunch of other things, but maintains the promise. All those layers are necessary, they're everywhere, but sometimes they get in the way, and this was a great example. If you want to dive into this particular layer getting in the way, I've got a great reference for you. And I just want to call out, because I'm interested in these concepts, so I'm going to impose this on you. There's another similar, analogous improvement that we've made in our data centers where TCP was getting in the way of very high-speed clusters, especially like machine learning, HPC clusters, and all the issues, similar issues that you get on the low-speed, high-latency networks. Even in a high-speed, low-latency network, we still struggle with a lot of limitations of TCP. So we invented a whole new protocol called Scalable Reliable Datagram, implemented that in essentially our hardware layer of the Nitro system, and we now can do things like fan out within the data center. So you send one TCP packet down the stack, we take that and we multiplex it over multiple UDP connections through what's called a CLO network, which is a highly parallel data center network, recompose it on the far end, and you see what looks like one giant pipe between your servers, but actually it's a highly spread out, highly optimized system. Now that happens below the programming interface, so you don't have to change your API. You can use TCP or you can use some of the HPC programming models, and we do that all automatically. And also we do hardware level encryption within the EC2 network, so we didn't have to mess with TLS. You can use it, you don't have to use it, it's all encrypted anyway. And I've got a couple of real quick references. If you want to go dive deeper on these two very interesting, I would say sort of analogous innovations for abstraction, one on QUIC, great talk from reInvent by one of its inventors, his primary inventor, who now works for Amazon, and another one on SRD, a couple of video as well as an academic paper that talks about how we made the data center network work so fast. And finally, we've actually begun to implement QUIC in our systems. The first and best place to put it is in CloudFront, because that's the front end to many clients, often across flaky and low latency or high latency networks. And so you can even today deploy a QUIC as one of the supported protocols on your CloudFront distributions. Going forward, we'll look at other services. ALB would be a logical, I'm not making any commitments here, but that would be a logical place to add QUIC. And maybe eventually in our API endpoints, again, it's not quite as many reasons to do it for EC2 described instances as it would be for a very chatty web scenario, but it's still the case that when you're dealing with, again, high latency, lossy networks, QUIC can really improve performance, and that could be interesting and applicable, especially for data plane APIs as opposed to control plane. So with that, I'll call it to an end. I want to thank you very much for coming. I hope you enjoyed the talk and learned something, and we'd be happy to follow up with you. We'll stay around for questions, and I hope you have a great Inforce. Thanks very much.